Let us talk about the effects of organic chemistry and what are the various effects that work in the organic chemistry. When we talk about carbon, let's see, we talk about the position of the carbon in the periodic table. Carbon is a member of the second period. The first element of the second period happens to be lithium. Above that is hydrogen. Then we have lithium, beryllium, boron, and then we have carbon, nitrogen, oxygen, fluorine. We do not talk about neon because neon is a noble element, noble gas. It does not take part in any reaction, so there is no use talking about neon. When we talk about lithium, beryllium, boron, carbon, nitrogen, oxygen, and fluorine, let's talk about the various properties of these elements. First of all, we talk about the outermost electronic configuration. Electronic configuration we talk about. Then lithium has one electron in the outermost shell, fluorine has seven electrons in the outermost shell, carbon has four. As you can very well see, it's the average of the two. 1 plus 7, 8 divided by 2 is 4. That is, out of the two extremes, carbon is right in the middle. Now we talk about something called the electronegativity of carbon. Lithium has the electronegativity again of 1. Fluorine has 4. 1 plus 4 is 5. Divided by 2, it gets 2.5. The electronegativity of carbon again happens to be right in the middle of lithium and fluorine, and it turns out to be 2.5. Let's talk about ionization energy. Lithium has ionization energy of 520 kilojoules per mole. Fluorine has 1680 kilojoules per mole. The average of the two will turn out to be 1100. Carbon has an ionization energy of 1086 kilojoules per mole, near about in the middle. Now, what does it mean? What does it tell us? If we talk about the valency, that is the capacity to form the bonds. If we talk about the valency, then lithium has a valency of 1, fluorine has a valency of 1, and carbon has a valency of 4. So that's what we get. Now, when we talk about these properties of carbon, it would mean that carbon does not have any tendency to form the ionic bonds. Lithium has a capacity to lose the electron. Fluorine has a capacity to accept the electron, while carbon doesn't have a tendency to accept or lose the electron. In fact, carbon likes to share the electron. The most stable compound of carbon are covalent compounds. More the ionic character in any of the compound of carbon, more unstable it becomes. So carbon dominantly forms covalent compounds. Further, let's talk about one property of carbon, and that is what we call as hybridization of carbon. Carbon has a capacity to show a hybridization of sp, sp2, sp3, depending on the various compounds. Different compounds have different kind of hybridization. Now, this hybridization, obviously, we understand that it affects the angle and the shape of the molecule. But hybridization also affects a very, very important property, and that is what we know as the electronegativity. Let us consider the various hybridization. And before the hybridization, let us consider the definition of electronegativity. Electronegativity is the tendency of an atom to attract the shared pair of electrons towards itself. More electronegative an atom is, more are the electron pairs of the bond shifted towards that atom. As the electronegativity of an atom increases, since the electrons are moving towards the atom, the bond length decreases. More is the electronegativity, lesser would be the bond length. So bond length also gives us an idea about the electronegativity. That is the reason why if on electronegativity scale, that is Pauling scale, if we talk about the electronegativity of nitrogen and chlorine, then both have the same numerical value. But effectively, nitrogen becomes more electronegative than chlorine because nitrogen has a smaller size. Due to its smaller size, effectively nitrogen's electronegativity becomes more than that of chlorine. Now here when we talk about carbon, let us consider that this is the nucleus of carbon. Here is an s orbital and here is the p orbital. When we talk about the s and the p orbital, let's talk about hybridization. Considering the sp hybridization, let's say we consider the p orbital directly, only the p orbital, then p orbital, the electron would be here. If pure p orbital is supposed to form the bond with an atom, it will be forming the bond in at this distance. It will be the farthest. If the bond is to be formed with the s orbital, this would be the position of the electron. Now, if the bond is to be formed by sp hybridized orbital, then sp hybridized orbital would be right in the middle of the bond formed by the s orbital and the bond formed by the p orbital. So this would be the sp orbital and the electron pair if it is present in the sp hybridized orbital. If it is to be sp2, then the p character would be increased. The sp2 would be a slightly farther away as compared to sp. So this would be the sp2 hybridized orbital. And if we talk about sp3 hybridization, then sp3 would be still further away as compared to sp2. As we can very well see, as the p character in the hybridization increases, or rather we can even say as the s character in the hybridization decreases, the distance of the shared electron pair from the nucleus of carbon increases. The electron is moving away from carbon, and as per the definition of electronegativity, we can even say that as the s character in the hybridization decreases, the electronegativity decreases. So much so that we have a tendency to say that sp hybridized carbon is more electronegative as compared to sp2 hybridized carbon, which is in turn more electronegative as compared to sp3 hybridized carbon. So electronegativity of the carbon, and with that the chemical properties of carbon, keep on changing with the hybridization of carbon. sp hybridized carbon, sp2 hybridized carbon, and sp3 hybridized carbon have absolutely different, unique chemistry of their own. So that's what we have as hybridization of carbon. Now let's talk about the various effects that work in organic chemistry. When we talk about the various effects in the organic chemistry, we can broadly classify the effects in two categories: the plus effect and the minus effect. When we talk about the plus effect can be written as simply plus. The plus effect is the effect which increases the electron density in the atom to which a group is attached or a group is approaching or influencing. If a group increases the electron density in the atom to which is attached, approaching, or influencing, the group is termed to be the plus group. And if a group is doing opposite of that, that is the group which decreases the electron density in the atom to which it is attached, approaches, or influences, then it is termed as the minus group. So we have two categories of the groups in the organic chemistry: plus group and the minus group. Please understand one thing very clearly, that the plus and the minus is not an absolute demarcation. A group could be behaving as a plus group in one situation and a minus group in the other situation, while it might not be influencing the electron distribution in the third situation. So, depending on the case, the group could be minus, plus, or non-affecting as per the situation. Now, once we have understood the plus and the minus effect, let's get along with the various named effect in the organic chemistry. Again, these effects could be classified into two further categories. That is, we can have permanent effects and we could have temporary effects. The permanent effects, which are the property of the molecule itself, they affect the melting point, boiling point, solubility, these effectors, and they are not influenced by any external factor, that is for the temperature, pressure, or the presence of other groups. So those are what we term as the permanent effects. But we do have some temporary effects also, the factors which work depending on the groups surrounding a given species. If you change the group surrounding the given species, the factor is going to change. It can become nullified or it could become opposite. Let us start with a effect called inductive effect. When we talk about inductive effect, we generally talk about a simple example. Let us say we talk about CH3, CH2, CH2, CH2 attached with fluorine. Let us consider what the effect of fluorine is going to be on these groups. Fluorine carbon bond is going to be a polar bond in which Fluorine is going to have a partial negative charge, while the carbon is going to have a partial positive charge. Carbon CH2 and fluorine bond is a polar covalent bond. It would be having a certain dipole moment. As far as chemistry is concerned, the dipole moment is from the positive towards negative. That is, we are talking about the shift of the electron. So this is going to be a polar covalent bond. Further, we can even talk about electronegativity definition as the tendency of a species to attract the shared pair of electron, or we can consider it to be the electron deficiency. More electron deficient is a species, more electronegative it becomes. In this particular definition, more would be the positive charge on a species, that much more electron deficient it would become, and that much more would be its tendency to attract the shared pair of electron. So, more positive a species is, more electronegative it is. In this case, in this particular compound, the CH2 having a delta positive charge is sp3 hybridized. The carbon attached to it also is sp3 hybridized. By all reasons, these two carbons should have exactly the same electronegativity. But due to the attachment of fluorine on the CH2, this carbon has gained a slight positive charge. Because of this slight positive charge present on the carbon, it will have slightly higher electronegativity as compared to the carbon attached to it. So this particular carbon also would pull the electron cloud towards itself. When the carbon CH2 having a delta positive charge pulls the electron cloud from CH2, it will further introduce a positive charge on the carbon. This positive charge would be much smaller than the positive charge on the carbon attached to fluorine. We can say it is delta of delta positive, a smaller positive charge. This carbon in turn will pull the electron cloud from the adjacent carbon, giving this also a small positive charge, and this factor would keep on moving. At every step, the positive charge being produced on the next carbon or the next atom would be reduced. The influence is going to decrease. Most of the time, this kind of an influence is ignored after four bonds. Here, what we get is a bond is being polarized. A covalent bond is being polarized due to the presence of a polar covalent bond. The polarization of a bond due to the presence of a polar covalent bond is termed as inductive effect. This effect travels through the bonds. So as the distance increases, as there are more number of intervening bonds, the factor, the influence decreases. And most often this influence is ignored after four bonds. In this case, fluorine is going to pull the electron cloud from the carbon it is attached to and decreases the electron density on that carbon. Hence, fluorine in this case is a minus I group, whereas alkyl group is going to push the electron in fluorine. It is going to increase the electron density in fluorine, and therefore the alkyl group in this case is a plus I group or the plus inductive group. The inductive effect is completely dependent on the difference in electronegativity. More electronegative a group is, more minus I it becomes, and less electronegative or more electropositive a group is, more plus I or plus inductive group it becomes. The minus I effect decreases the negative charge on a species, increases the positive charge on a species, whereas plus I group decreases the positive charge on the species and increases the negative charge on the species. The minus I effect stabilizes the negative charge, while plus I effect stabilizes the positive charge. Having talked about the inductive effect, let's get along with another factor called conjugation, conjugative effect, or resonance effect. Now let's talk about a simple example. Let's talk about CH2 double bond CH2. This is ethene. Let's talk about how ethene gets the double bond, the pi bond. Here we have carbon, carbon, single bond, and here we have the hydrogens attached to it. Here we have the hydrogens attached to it. Now, one of the p orbital of carbon is not taking part in hybridization. This p orbital will be perpendicular to the plane of the molecule. Here we get the p orbital. This is the p orbital that we have. Now, this p orbital contains unpaired electron with it. This carbon, they have a tendency to attract the shared pair of electrons towards themselves. When they attract the shared pair of electrons, or rather, I should say, they attract the unpaired electron present on the other carbon towards themselves. So, this electron cloud will be shifted towards this carbon, the nucleus. This electron cloud will be shifted, and these electron clouds will get deformed. When they get deformed, here we get these two carbons. Now I am not writing the hydrogen because I am only concerned with the orbital. This orbital is going to be deformed. The other orbital is also going to be deformed. These orbitals are going to overlap with each other. When these orbitals are going to overlap with each other, the electron cloud is formed above and below the plane of the molecule, and this will constitute a pi bond. These are the pi orbitals, and they form the pi bond. That is how the ethene molecule is formed. The pi orbital in case of ethene is formed. Let's talk about another molecule. Let's talk about buta-1,3-diene. In case of buta-1,3-diene, what we find is here also we can consider the same way the orbital being formed, the bonds being formed. We have the carbons. Each of these carbon contains the unshared electron pair, electron and an unhybridized orbital. These unhybridized orbital when we discuss, as in the previous case, there is again an attractive force between these electrons and the nucleus. As is suggested by the structure, if we number these carbons, this is one carbon, this is the two carbon, this is the three carbon, this is the four carbon. The 1 and 2 carbon attract the unshared electron of each other towards themselves. Similarly, 3 and 4 carbon also attract the unshared electron, and that would form the overlap of the orbital and the pi bond. Now, this is how we can consider the structure buta-1,3-diene. But now the question arises that will the carbon number 2 and 3 attract the electrons of each other? Why should they not? The nucleus is positively charged while the electron cloud is negatively charged. So there is an attractive force between the carbon 2 and 3 as well. If we consider all these attractive forces, the deformation of the electron cloud takes a different structure altogether. Here we have the four carbons. The electron cloud of the carbon number 1 will be deformed towards the carbon number 2. The electron cloud of carbon number 4 would be deformed towards the carbon number 3. The electron cloud of carbon number 2 will be pulled from two sides, and since it is being pulled from the two sides, it will deform in this manner. It will be deformed towards the carbon number 1 as well as carbon number 3. In the same manner, the electron cloud of carbon number 3 will also be deformed similar to the electron cloud of carbon number 2, and it would be spread. So now what we can see is that all the four orbitals, they overlap with each other, forming a continuous passage for the electrons. Let us consider how much electron is going to be provided or assigned to each carbon. Considering that, here we create the compartments. The electron of carbon number 1 will be completely contributed towards the first bond. So here there are two electrons in the sigma bond. There is one electron being contributed from the carbon number 1, and half electron will be contributed from the carbon number 2, because the electron of the carbon number 2 will be shared between carbon number 1 as well as carbon number 3. So here we talk about the total number of electrons present between the two carbons, carbon number 1 and 2 is 3.5. We understand that two electrons make one bond. So 3.5 electrons are going to make 3.5 divided by 2 equal to 1.75 bonds. In the same manner, if we talk about the carbon number 4 and carbon number 3, here again we are going to have two electrons in the sigma bond between the two carbon, one electron being provided by the carbon number 4 and half electron being provided by the carbon number 3. So here again we have 3.5 electrons and we have 3.5 divided by 2, that is 1.75 bonds. When we talk about the carbon number 2 and 3, half electron is being provided by the carbon number 2. Half electron is being provided by the carbon number 3. There are two electrons in the sigma bond. So total electrons which are assigned to carbon number of 2 and 3, the bond between them would be 3. So the bond, if we talk about, it is going to be 3 by 2, and that is 1.5 bond. Now what we can understand is due to this kind of a factor, that is the overlap of the unhybridized p orbital, which allows the electron cloud to move over the entire molecule, has led to the formation of partial double bonds. We do not have any single bond between the carbons, and we don't have even a double bond between the carbon. What we have is a partial double bond, which is somewhere in between 1 and 2 bonds. The bond length would be smaller than the single bond but larger than a double bond. The bond strength would be larger than a single bond but lesser than the double bond. So here, the electron cloud has got delocalized over the entire molecule due to the overlap of unhybridized orbitals, most often p orbitals. This particular delocalization is termed as conjugation. The spreading or delocalization of the entire electron cloud over the entire molecule or a part of it due to the overlap of unhybridized orbitals is termed as conjugation. So this particular alkene, that is buta 1,3-diene, is conjugated. This conjugation spreads the electron, makes the species more stable in this case, so it is preferred. Now, when we talk about conjugation, there are certain conditions that the molecule must satisfy for conjugation to take place. The very first thing is that when we talk about conjugation, the orbitals have to be parallel to allow them to take part in conjugation. So we can say only parallel orbitals can conjugate with each other. When we say parallel orbital, then there are two corollaries. The very first corollary would mean that the part of the molecule which is conjugated, which is taking part in conjugation, must be planar. It must be planar, otherwise the orbitals are not going to be parallel. So if we want to say that a particular system, that particular part is conjugated, then we also say that that particular part is planar. So that is the very first thing that is required. Further, one atom cannot have two orbitals parallel to each other. That is why one atom can never contribute two orbitals towards the same conjugation. Every atom taking part in conjugation will contribute exactly one orbital towards that conjugated system. So that is the first case of conjugation. Now to talk about the second condition of conjugation.